Greetings students, welcome to today's lecture. We'll talk about simulated annealing search in today's lecture. Now, after learning about the hill climbing search, we have seen some drawbacks of that search process. Let's think of a state space where we are currently at a local maximum. And right beside this, we have a global maximum. So let's say we are currently at state 0. In order to reach the goal state, we need to make a downhill movement. Let's say to state 1. So when a hill climbing search cannot make a downhill move towards a state with lower value, it is guaranteed to be incomplete because it will always settle down with the local maximum value instead of searching for the global maximum value. So that means we have proposed an approach to escape the local maximum. In order to escape the local maximum, we need to allow the bad moves. But we also need to make sure that the probability of making bad moves will reduce with time. Okay. So now let's talk about it. So for the reason that I've stated before, this is one of the reasons why hill climbing search gets stuck in a local maximum, since it cannot make a downhill move. So in contrast, let's think of a purely random walk. So when I'm talking about random walk, we are totally unaware of the goodness or badness of the move. Let's say we are just making a move randomly. We are just selecting a state randomly from its successors. But what will be the problem of selecting a random state? The problem of selecting a random state, that means if we uniformly move randomly to its neighbors from the set of successors, it is complete. But it is extremely inefficient as we are not considering the goodness or badness of the moves. So therefore it is reasonable to try to combine the hill climbing search with random walk in some ways that yields both efficiency and completeness. So what we want to do here, at first we need to escape the local maximums by allowing bad moves. But in order to accomplish this, if we try to perform a random walk, that means all kinds of bad moves will be allowed irrespective of its goodness or badness value. So we also need to make sure that this is not as bad as a random walk. So simulated annealing is such an algorithm that incorporates the concepts from both hill climbing search and random walk. So it tries to make the approach more complete and efficient at the same time. So in metallurgy, what do you understand by the word annealing? In metallurgy, annealing is the process used to temper or harden metal or glasses by heating them to a higher temperature and then gradually cooling them down, thus allowing the metal to coalesce into a low energy crystalline state. So to understand the simulated annealing, let's switch point of view from hill climbing to gradient descent. So what was the basic difference between hill climbing and gradient descent? In hill climbing search, we try to maximize the objective function. Therefore, our aim in hill climbing is to find out the global maximum value. But on the contrary, in the gradient descent algorithm, what we try to achieve? We try to achieve the minimum value in order to minimize the cost. That means, therefore, our aim for gradient descent algorithm would be to find out the global minimum value. So imagine we're trying to find out the global minimum value in a bumpy surface. Now how do you do that? Let's think of rolling a ping pong ball from here. So we're basically letting the ball roll into the deepest crevice of the bumpy surface. So here we have one global minimum value, which is our goal, to reach the ball to that state. But unfortunately, what might happen here, the ball may get stuck in the local minimum values. So how do you get the ball out of this local minimum value? So instead of letting the ball roll, when it will come to the rest at a local minimum value, we need to shake the surface. We need to shake the surface just hard enough to bounce the ball out of the local minimum value. So if we shake the surface hard enough, then the ball will get out of this local minimum value and it will start rolling again, and eventually it will reach the global minimum value. So we need to shake it hard, but not hard enough to dislodge it from the global minimum value. So we need to make sure the intensity of shaking should decrease so that the ball may not get out of the global minimum value. So if you think of this rolling ball analogy, it might help you understand the concept better. So at first we'll start shaking hard to make sure that the ball may get out of the local minimum values, but eventually we'll start shaking less. That means whenever we'll be shaking less, we'll try to make sure the ball shouldn't get out of the global minimum value, it should stay there instead. So at first we keep the value of t high, then we start decreasing the value of t slowly, so that whenever we reach the best state, we can settle for the most optimal solution. Okay, so if I try to summarize the whole concept, the simulated annealing solution is to start by shaking hard, keeping the temperature high, and then gradually reduce the intensity of the shaking by lowering the temperature. Now students, let's look into the simulated annealing algorithm. The innermost loop of the simulated annealing algorithm is almost similar to the hill climbing algorithm. But in hill climbing algorithm, what we did, we picked the best move. But here, instead of picking the best move, however, it picks a random move. You can see here, we're picking a random move from the list of the current successors. Okay, so, and then you can see two values here. Small t indicates the current time, and capital T indicates the current temperature. So according to the analogy described in the previous part of the video, what we're trying to do, with time we're going to decrease the temperature. Initially, at the beginning, the temperature will be high, and after a large number of iterations, when the time value increases, the value of temperature will decrease, and eventually we will reach to a temperature of value 0. Whenever the temperature value reaches 0, we'll immediately stop the iterations. So this can be compared to the previous analogy. At first, at the beginning, we'll start shaking hard, that means the temperature value would be high, and eventually at the end we will keep on decreasing the temperature value to 0, which basically resembles the simulated annealing process. Okay, so let's see if the move improves with the situation. Let's see, we're currently at state 0 and we are looking for state 1. That means the current value is state 0 and the successor that we picked randomly is at state 1. So here we can see the successor, that means the next state, has higher value than the current state. When the next state has a higher value than the current state, we know that the move improves the situation. So whenever the move improves the situation, it is always accepted. And if the opposite happens, let's say we have now reached to state 1 and now we have immediately picked a neighboring state, state 2. Now state 0 is represented as the current state and state 1 is represented as the next state. So after picking the next state randomly, we count the value. To be specific, we have counted the goodness value, and we see that the next state is not improving the situation. So the algorithm accepts the move with some probability less than 1. The probability decreases exponentially with the badness of the move. Here del E corresponds to the badness of the move. Okay, so how the move is exponentially decreased? It is exponentially decreases to the amount of del E by which the evaluation is worsened. If the evaluation is worsened, then the del E value should be less than 0, which indicates a negative value. Let's say for the higher temperature, let's calculate the probability value. For higher temperature, whenever we're trying to calculate the probability value, let's say the value would be E, and since we're making a bad move, the del E value should be less than 0 divided by a higher temperature. Let's say the higher temperature is 400 for now. So let's calculate the value of probability. So the probability value is very close to 1. That means 0.99. So at higher temperature, we're always accepting a bad state. But what happens when we're making multiple bad moves and the temperature lowers with time? When the temperature reaches to 50, what happens? The probability value decreases to 0.98. Okay, so what we have seen here, the bad moves are likely to be allowed at the start when the temperature is high, and they become more unlikely as the temperature decreases. For lower values, you will keep on seeing that the value of probability keep on decreasing. Okay, and they become more unlikely as temperature decreases. And so one can prove that if the schedule lowers the temperature slowly enough, the algorithm will find a global optimum value with the probability approaching 1. So simulated annealing search was first extensively used to solve the VLSI layout problems in the early 1980s. And it has always been applied widely for factory scheduling problems and other large-scale optimization problems. So I hope this will give you a better idea about simulated annealing process.